5.0.0 Connections and terminal markings for AC motors. Identify the connections and terminal markings for AC motors. Identify the terminals for Y-connected motors. Identify the terminals for delta-connected terminals. So the markings on the external leads of an induction motor are sometimes missing or illegible. Proper identification must be made before the motor can be connected to the line. This section describes procedures for identifying leads in three-phase motors. The required materials for this procedure are appropriate PPE, 12-volt DC battery such as an automotive battery, analog meter with large scale and low range. Digital meters may not clearly capture the voltage kick. Test leads and jumpers, momentary contact, normally open, push button switch. Labels to mark leads as they are identified in three-phase 9-lead induction motors. Before starting, identify whether the motor to be tagged as Y-connected or delta-connected. Compare the two connection diagrams, figures 61 and 62. You'll see that both types of motors have 9 leads and 6 coils. If a Y-connected motor, 3 coils are connected and 3 coils are isolated. A delta-connected motor has 3 sets of 2 coils, each connected. So here's a Y-connected motor. Let me start by saying Y and delta are not real things. You'll never open up a motor or a transformer. You'll never see a delta. You'll never see a Y. It's a pictorial representation of the relationships of the coils. So this would be what you'd see. Well, this is what would be typical of a Y-wired motor, WYE. It only has 9 leads in the junction box on the side of the motor because 3 of them have been put together and buried. They buried them. They took 10, 11, and 12 and tied them together in a star pattern, and they buried them. So the leads we see are 1, 2, 3, 4, 5, 6, 7, 8, and 9. We can hook these up in series just by hooking up 4 to 7, 5 to 8, and 6 to 9 for high voltage, or we can hook them up in parallel for low voltage. I'll show you on the magic board. Here's delta. It's got 3 sets of 2 coils tied together. Again, 10, 11, and 12 aren't here. They took 10 and tied it with 2. They took 11 and tied it with 3. They took 12 and tied it with 1. So all we see are 9 leads, but there are 6 coils, each with 2 ends, so there are 12 leads. 3 of them are hidden. All right, let's go ahead and talk about this, because inquiring minds want to know. So again, what we said is that I'll try to use brown or yellow. There. These are our high voltage incoming lines. Brown, orange, and yellow. Black, red, blue is for 120, 240. Brown, orange, yellow is for 240, 480. I'm not going to bother with the ground, so we're not going to show the ground. What happens is we have these motor leads. Here are 2 coils. Here are 2 coils. And here are 2 coils. Now, I'm going to copy everything so I can, oh, what the heck is this? try this again. What is this thing doing? In here, I want to control all, control copy, go to the next page, and paste. There we go. All right. And I'm going to go to the next page and paste again. And it's not going to work, and that's nice. Control copy, control paste, control copy, control paste. All right. Let's see how that works. We get back to our main page here. So we're going to talk about a Y configured motor first. And again, I'm going to draw these coils. And it's a pictorial representation. It's not, you'll never see a delta. You'll never see a Y. The numbering system is 1, 4, 7, 2, 5, 8, and 3, 6, 9. So that if I wanted to connect this motor in high voltage, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I wanted to connect this motor in high voltage, I would hook it up in series. So I'd put a jumper between 4 and 7, 5 and 8, and 6 and 9. So 4 to 7, 5 to 8, 6 to 9. And 1, 2, and 3 would be my leads out. 1, 2, and 3. So on here, we have, and I'll have to draw the numbers small, 1, 4, 7, 10. Well, that 10 is already used. 2, 5, 8, 11, 3, 6, 9, 12. So 10, 11, and 12 have already been hooked together. There, those are hooked together. And what we'll do is we'll take 4 to 7, 5 to 8, 6 to 9, and 1, 2, and 3 are going to be our leads out. So I'll take 1 to A phase, and I'll take 2 to B phase, and I'll take 3 to C phase. And now this motor's hooked up for high voltage Y. High Y. And if I wanted to hook it up low voltage Y, I should have done a lot of this off screen, but 2, 5, 8, 3, 6, 9. Again, we've got 10, 11, and 12 are already hooked together in the Y configuration. This is low voltage Y, and we're going to hook it up in parallel. You hook it up in series for high voltage, you hook it up in parallel for low voltage. And in order to do that, we're going to draw an airplane propeller. And here's how you draw an airplane propeller. You leapfrog over the second, then go to the third, and you do that. That's an airplane propeller. So I'm going to take this and go whoop, whoop. I'm going to take this whoop, 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 whoop. And so what we have is 1 goes to 7, 2 goes to 8, and 3 goes to 9. 4, 5, and 6 meet together in the middle for the star. There's 4, 5, and 6, and they're hooked together. And 1, 2, and 3 are our lines out. So let's try to do that here. I'm going to use a different color. So I'm going to take 1 to 7, 2 to 8, and 3 to 9. And 4, 5, and 6, I'm just trying to not be confusing here. 4, 5, and 6 are going to tie together. There's 6, there's 5. So 4, 5, and 6 are tying together. And I actually didn't need this red in here, but that's okay. So let me go blue there, and then black there. So here's 1 to 7, 2 to 8, 3 to 9, 4, 5, and 6 are tied together. And then we're going to use 1, 2, and 3 as our power out. We'll go to A phase, B phase, and C phase. There. So that's how we connect low voltage and high voltage for Y. Remember, you put them in parallel for low voltage, you put them in series for high voltage. Delta is the same story. We're going to draw these 6, and here's 1, 4, 7, and this is 10 and 2, 5, 8. This is 11 and 3, 6, 9. And this is 12 and 1. But those have already been buried. So we have 1, 2, and 3, 4, 5, and 6, and 7, 8, and 9. And I wonder if I can grab all this and copy, and go to the next page and paste. There we go. Maybe that saved us a little bit of time. So again, if we're talking about high voltage, 240, 480, we're going to hook it up 480. We're going to hook it up high delta. High delta. Again, we're going to go in series. We'll go to 4 to 7, 5 to 8, 6 to 9. Here's 4 to 7, 5 to 8, 6 to 9. 1, 2, and 3 are our leads out. So here we're going to take 4 to 7, 5 to 8, and 6 to 9. And one goes to A phase. And remember, 10 and 2 are tied together. So I'm going to take 10 to B phase and 2 to B phase. And I'm going to take, on this second one, 11 goes to C phase, and 3 goes to C phase, and 12 goes to A phase. So that's high voltage for delta. We're going series for high voltage. Series because if this is 240 volts and this is 240 volts, when I tie the two of them together, they're good for 480 volts. So we'll put them in series, and then we can put 480 volts across them, and we can feed this motor. We won't burn it up because each coil is only seeing 240 volts. And if we wanted to go low voltage, Y, we'll go low voltage Y. I'm sorry, delta, excuse me. We're going delta. Low voltage delta, excuse me. There, we're doing delta. Then we're again going to go in parallel. We'll go 1 to 7. Boom, this goes here, this goes to here, this goes to here. I know this is a horrible drawing. I'm sorry. I'm trying not to waste too much time. 1 goes to both 6 and 7. If you look at that, 1, 6, 7. So 1 goes to 6 and 7, and 2 goes to 4 and to 8, 2, 4, 8, and 3 goes to 5 and to 9, 3, 5, 9. So 1, 6, 7, 2, 4, 8, 3, 5, 9, and 1, 2, and 3 are our leads out. So we're going to do that where we take brown, 1 goes to A phase, and 1, 4, 7, 2, 5, 8, 3, 6, 9. So 6 also goes to A phase, right? And then 7, 1, 4, 7, there, this one goes to A phase. Here, let me just put the numbers in for you. 1, 4, 7, 10, 2, 5, 8, 11. And you won't see these 12 leads. You'll only see 9 leads. So they've already taken 10 and tied it with 2. And they've taken 11 and tied it with 3. And they've taken 12 and tied it with 1. So I hope that I'm not confusing you by drawing it this way. So 1 goes at 6 and 7. 1, 6, and 7. 2, so this is going to be B phase, orange, is 2, B phase, 4, B phase, and 8, B phase. I need a darker orange than that, sorry. Let me try this one more time. There we go. We'll do a little bit darker orange. Wasn't quite dark enough. And then 2 and 10, so this 10 also goes. And then 3, 5, 9. So 3 goes to C phase. Oops, wrong one, sorry. 3 goes to C phase, 5 goes to C phase, 9 goes to C phase, and 11 and 3 are tied together, so it also goes to C phase. So now it's very easy to see A to B, A to B. Those are in parallel. B to C, B to C. Those are in parallel. C to A, C to A. Those are in parallel. Okay, so there's your delta low. So to recap, and I'm sorry I'm being so lengthy today. Again, here in Y, this is good for 240 volts, and this is good for 240 volts. And you can put it across 480 when it's in high voltage. So you go 4 to 7, 5 to 8, 6 to 9. 1, 2, and 3 are your leads out. When we go to low voltage, we'll go in parallel. So it ends up that 1 goes to 7, 2 goes to 8, 3 goes to 9, 4, 5, and 6 tie together. And again, if this is good for 240 volts, and this is good for 240 volts, well, anyway, they're tying together, and you're not putting 480 volts across them. You're only putting 240 volts across it. So it doesn't end up putting double the voltage on it. And then in delta, if we go high, again, 4 to 7, 5 to 8, 6 to 9, A to B, B to C, C to A, that's delta. A to B, B to C, C to A. And low voltage is A to B in parallel, B to A to B, B to C in parallel, C to A, C to A parallel. I hope you got something out of that. I usually am better at it than that. But let's go back to the book, because they were telling us about delta and Y. So here are your 9 leads for delta. Again, it's 12 leads, but 3 of them are hidden. 10 and 2, 11 and 3, and 12 and 1. All right. Using an ohm meter, insulate all motor leads from one another and check for continuity between each lead. Start by placing one probe on one lead and continue this process to check through the remaining leads. As you identify which leads show continuity, group them together. Continue this procedure with each lead until all leads are grouped. So again, if you find continuity between three groups of three. If you have continuity between 4, 9, and 1, that's a group, and 7, 2, and 5, and 8, 3, and 6, then you know that this is a delta motor. If you have continuity between 7, 8, 9, but you don't have continuity, the other three are isolated, you have 1 and 4, 5 and 2 and 5, 3 and 6, then you know it's a Y motor. But we also have to figure out which way they run, because you don't want them to go backwards. So, Y-connected motor terminals, coil arrangements, and a Y-connected motor. So there again, here's 1, 4, 7, 10, and the 10 is buried. 2, 5, 8, and 11. 3, 6, 9, and 12. So they've got these arranged so that they can hook them up either in series or in parallel. Take the group of three common leads and in no particular order identify them as leads 7, 8, and 9. So the three that had continuity, we're going to designate them as 7, 8, and 9. Using the diagram of figure 64 as a guide, connect the positive lead of the battery to lead 7. Connect the negative lead from the battery through the normally open switch to leads 8 and 9 simultaneously. So there's 8 and 9. And there's their momentary switch. It says connect one of the three remaining lead pairs to the voltmeter terminal. Close the normally open switch while observing the DC voltmeter. Use the lowest scale practical without overranging the meter. If the meter deflection is upward, note the voltage reading. Observe that the reading occurs only on the initial energization of the winding and then decays. Note the peak reading only and ignore the deflection in the opposite direction that occurs when the switch is opened. If the meter initially deflects downward, reverse the test leads and try it again. Continue with the remaining two lead pairs. The pair with the highest voltage reading is the winding associated with lead 7. The lead with a positive polarity is identified as lead 4, and the lead with a negative polarity is lead 1. Repeat step 3, but apply the positive lead battery to lead 8 and the negative lead of batteries to leads 7 and 9. The positive lead of the pair with the highest voltage is identified as lead 5, and the lead with the negative polarity is lead 2. Repeat steps 3, but apply the positive lead of the battery to lead 9, and the negative lead of the battery to leads 7 and 8. The positive lead of the pair with the highest voltage is marked lead 6, and the negative lead is lead 3. All right. To confirm that all leads are correctly identified, connect the motor to the circuit. Be sure to observe proper connection procedures for the applied voltage. After connecting the motor to the circuit, start the motor and take current readings on all three lines. If the motor starts correctly and the current readings are approximately equal, the procedure was a success. Delta-connected motor terminals. A delta-connected motor has three sets of three leads. Figure 65 shows how the coils are arranged in a delta-connected three-phase motor. In this figure, the coils that are side by side are wound on the same poles of the motor. As discussed previously, this will allow some transformer interaction between the adjacent coils. To identify the terminals of the delta-connected motor, proceed as follows. So the same thing. Using an ohm meter on a low scale, measure the resistance between each of the three leads in one group. When performing this measurement, you should see that the resistance between two of the leads is about twice that between either of the other two and 3. The lead that shows the least resistance to the other two will be lead 1. Refer to all three wires in this set as set 1. Repeat step 1 with the second setup to identify the lead with the least resistance as lead 2. Refer to all 3 wires in this set as set 2. Repeat step 1 with the final set of leads to identify the lead with the least resistance as lead 3. Refer to all 3 wires in this set as set 3. Using the diagram as a guide, connect lead 1 to the positive terminal of the DC voltage source and one of the remaining leads in that set to the negative terminal. Attach the red positive lead of the voltmeter to lead 2 and the black negative lead to one of the 2 unknown leads in set 2. Press the push button and observe the meter needle. If the correct leads have been selected, a voltage will be induced into this coil. If not, connect the second lead of the voltmeter and repeat the test. If there is still no induced voltage, disconnect the unknown lead in set 1 from the DC voltage and connect the remaining unknown lead to the negative source. Repeat the test until the leads with an induced voltage have been identified. When these leads are located, identify the lead connected to the negative terminal of the DC voltage source as lead 4 and the lead connected to the negative voltmeter probe as lead 7. Identify the other lead in set 2 as lead 5. All right. This is the unknown lead for group 1. The remaining lead in set 1 will be lead 9, leaving lead 1 on the positive DC terminal. Connect the negative terminal to the lead 9. Attach the red lead of the voltmeter to lead 3 and the black lead to one of the 2 unknown leads in set 3. Press the push button and observe the meter needle. If the correct leads have been selected, a voltage will be induced into this coil. If not, connect the second lead to the voltmeter and repeat the test. When these leads are located, identify the lead connected to the negative voltmeter probe as lead 6. All right, I'm not going to read that. Well, we've got 2 more steps. Let me just read them. The remaining lead in set 3 is lead 8. To verify this, connect lead 3 to the positive terminal of the DC voltage source and lead 8 to the negative terminal. Attach the red lead of the voltmeter to lead 2 and the black lead to lead 5. Press the push button and observe the meter needle. If the results are correct, a voltage will be induced into the coil, resulting in the meter needle deflection. And to confirm that all leads are correctly identified, connect the motor to the circuit. Be sure to observe proper connection procedures for the applied voltage. When the motor is connected to the circuit, start the motor and take current readings on all 3 lines. What I'm going to say is don't start the motor. Just bump it. Just apply a momentary burst of the 3-phase electricity. If it's 240 volts, hook it up to the 240 and just bump it. Push the start and the stop immediately after, just to see if it rotates. Listen for horrific noises. Try to observe it. If it sounds like it was trying to start, go ahead and push the start button and see if it runs. If it does, and it doesn't sound like it's under distress, go ahead and take your amp readings. Okay? But don't just start that motor. If it's not hooked up correctly, you might fry it. So a Y-connected motor has delta connected motor has, I'll let you answer those, 6.0.0. NEC requirements for motors. The best motors on the market won't perform if they're incorrectly installed. Therefore, everyone involved in motor installation must understand the various procedures. Motor installation often requires more than one craft. In addition to understanding how to make the correct and sound motor terminations, electricians also need to be aware of the related NEC installations and motor protection requirements. 6.1.0 Motor Installation. Article 430 covers the application and installation of motors, motor circuits, and motor control connections, including conductors, short circuit and ground fault protection, starters, disconnects, and overload protection. All motors must be installed in a location that allows adequate ventilation to cool the motor. Further, the motors should be located so that maintenance, troubleshooting, and repairs can be readily performed. Such work consists of lubricating the motor bearings or perhaps replacing worn bushings Testing the motor for open windings and ground faults may also be necessary from time to time. Elevated not less than 8 feet above the floor for 50 volts to 300 volts between ungrounded conductors. Elevated not less than 8 feet 6 for 301 to 600 volts, and elevated not less than 8 foot 7 for motors 601 to 1000 volts. In all cases, adequate space must be provided around motors with exposed live parts, even when properly grounded, to allow for maintenance, troubleshooting, and repairs. So here's a summary of NEC requirements for motor installation. The motors must be installed in areas with adequate ventilation. They must also be arranged so that sufficient space is provided for replacement and maintenance. 430.14a. Open motors must be located or protected so that sparks cannot reach combustible materials. 430.14b. In locations where dust or flying material will collect on or in motors in quantities that will seriously interfere with the ventilation or cooling of motors, causing dangerous temperatures, suitable types of enclosures, enclosed motors that will not overheat under the prevailing conditions must be used. Disconnecting means, I've got this highlighted. Motor disconnecting means must be within sight from the controller location and disconnect both the motor and the controller. That's 431.02a. Within sight means you have a straight line of sight to it and you're within 50 feet and it's not through doors or windows. The disconnect must be readily accessible and clearly indicate the on-off position. Motor control circuits require disconnecting means to disconnect them from all supply sources. The disconnecting means must be as specified in the code. Flexible connections such as type AC cable, flexible cord, flexible metal conduit, etc. are standard for motor connections because they vibrate. You can't just pipe into them with rigid conduit or EMT. It has to be flexible. All conductors of a remote motor control circuit outside the control device must be installed in a raceway or be otherwise protected. The circuit must be wired so that an accidental ground fault in the control circuit beyond the controller will not start the motor, nor will it bypass any safety shutdown devices. Exposed live parts of motors and controllers operating at 50 volts or more must be guarded by installing it in a room, enclosure, or other location to allow access only by qualified persons or be elevated 8 feet or more above the floor. Special requirements apply to ASDs and their motors. Motors operating over 1000 volts. Special installation rules apply to motors operating at over 1000 volts. And controller grounding, motor controller enclosures must be grounded. 430.244. All right, excuse me, yeah, that's adjustable speed drive. Special requirements apply for adjustable speed drives in their motors. That's 430 part 10. Summary of NEC requirements for motors, motor circuits, and controllers. So part 9 is disconnect motor controllers from the circuit. All connecting means, disconnecting means for the motor circuit must meet the requirements of NEC sections 430, 108, 109, 110. Continuous rating of 115% of motor full load current and must be located in sight of motor location and driven machinery. Protects branch circuit from short circuits and grounds. That's part 9. Used to start and stop motors. That's part 7. Protects motors and controllers against excessive heat due to motor overload. Is part 3. Specifies the sizes of conductors, cables, and carrying the motor current without overheating. Is part 2. All right. When a motor is received at a job site, always refer to the manufacturer's instructions and follow them carefully. Failure to do so could result in serious injury or death. Install and ground according to the NEC requirements and good practices. Consult qualified personnel with any questions or problems. Uncrating. Here's a highlight. It says measuring the insulation resistance with a megameter is a good way to test for dampness. So you should have a very high measurement on that. Lifting. Eye bolts for lifting lugs on motors are intended only for lifting the motor and factory motor mounted standard accessories. These lifting provisions should never be used when lifting or handling the motor when it is attached to other equipment as a single unit. Guards, rotating parts such as pulleys, couplings, external fans, and shaft extensions must be permanently guarded. Requirements: all motors must be installed, protected, and fused in accordance with NEC Article 430. For general information on grounding, refer to Article 250 and Article 430, Part 13. Thermal protection information. The motor nameplate may or may not be stamped to indicate thermal protection. All right. Motor protection. Fuses are normally used with motor overload protection. When used, fuses must be provided in each ungrounded conductor as well as the grounded conductor for a 3-wire, 3-phase AC system with one conductor grounded. When non-fuse overload protective devices are used, refer to NEC section 430.37 and table 430.37. Note that each motor winding must be individually protected against short circuits and ground faults. In general, when providing overcurrent protection for motor circuits against overcurrent due to grounds and short circuits, follow the guidance found in NEC section 430.52, NEC table 430.52C. Provides for time delay and instantaneous trip values of various types of motors and a percentage of full load current. NEC section 430.52C1A and B outline the possible exceptions to the NEC table values. Table 8 shows an example of relevant information for squirrel cage motors, but you must consult the NEC table for complete information. So here it's saying that if you have a squirrel cage motor other than design B, energy efficient or premium efficiency models, for non-time delay fuses, you're going to have 300% of the running current in those tables. Tables 430.247, 48, 49, and 50. Dual element time delay fuses, 175%. Instantaneous trip circuit breaker, 800%. That's why we don't like to use instantaneous trip circuit breakers to protect motor circuits. At inverse time circuit breakers, 250%. When sizing the overload protection for continuous duty motors larger than 1 horsepower, refer to NEC section 430.32A. Motors that have a service factor of 1.15 and or a maximum temperature rise of 40 degrees Celsius shall be provided with overload protection, limited to 125% of the full load current of the motor. This also applies to the secondary circuit of wound rotor motors. All other motors shall be limited to 115% of the full load current. And also, if you go to 430.6, it's going to tell you that you need to use the nameplate rating for the full load current to size the overloads. Most everything else you can use those tables, the table values, 430.247 through 250. If the desired overload ratings are not available when sizing overload protection for the motor, then use the next higher available overload rating. This is allowed provided that 140% of the full load current is not exceeded by the motor that has a service factor of 1.15 and or a temperature rise of 40 degrees Celsius. For all other motors, this maximum value will be 130% rather than 115% as stated earlier if it's having trouble starting. So those adjustable speed drives, the protection for adjustable speed drives is based on the rated input to the power conversion equipment. If overload protection is supplied with the equipment, then no further overload protection is required. The rating of this disconnecting means shall be no less than 115% of the rated input current of the power conversion equipment, and it shall be physically located in the incoming line. Thermal protection. A thermal protector, this is a highlight, integral to the motor, is often used to protect the motor from overloads and starting failures. All motors with a voltage rating greater than 1,000 volts must have a thermal protector, and its overload must not have an automatic reset feature. So thermal is heat. So if it's 1,000 volts or greater, you have to have a thermal protector, where if it heats up, it'll trip, it'll open the circuit, and it's not an automatic reset. You have to reset it yourself. So, and here it's 170% for full load current not exceeding 9 amps, 156% for full load current between 9.1 and 20 amps, and 140% of the motor full load current exceeding 20 amps. Branch considerations. According to NEC section 430.22, when a single motor used in a continuous duty application is supplied from branch circuit, the ampacity of the branch circuit must be not less than 125% of the motor full load current as determined by NEC section 430.6A1, or not less than required by NEC sections 430.22A through G. If a multiple speed motor is used, then the ampacity shall be based on the highest of the full load current ratings on the motor nameplate. Where motors have unusual duty cycle requirements, use the requirements listed in section 430.22E. All right. Let's see here. It says several motors loads are permitted to be provided from one branch circuit if all of the following apply. So you can feed more than one motor with one circuit. If the system voltage is less than 1,000 volts, the branch protective device protects the smallest installed motor. All motors on the circuit are not over a horsepower and less than 20 amps on 120 volts. Circuit where each motor draws less than 6 amps. Also, overloads must be installed on motors, and short circuit current, ground fault circuit current must not exceed the branch circuit rating if it's part of a factory listed assembly. So, in instances where taps are used, short circuit current and ground fault current protection may not be required for the taps used. This is true provided that the taps used has the same ampacity as the branch circuit to which it is connected. Additionally, the tap cannot be longer than 25 feet. 6.0.0 section review. Any exposed live parts of motors must be guarded if the motor, and per NEC section 430.32, the overload protection of a motor with service factor 1.0 must trip at. All right. This concludes 26202 motors, theory and application. Hope you got something out of it. If you did, give me a thumbs up. Consider subscribing to my channel. And as always, I'll see you on the next video. Thank you. Hey, this is Brian Young. If you liked my video, please give it a thumbs up and consider subscribing. I'll see you on the next video.